Up to this point, we know the cause of the change of the velocity of an object or the cause of the acceleration. It means that if there is an object and this object interacts with the environment and there is forces apply or act on this object. Okay, we have this force, maybe this is F1, F2, F3, F4, F5, and maybe more, and the mass of the object is m. So from the second law we can have the relation between this force and the acceleration as the summation of the force or the net force is equal to m times a. So we can write the acceleration a as a summation of f over m. Okay, and from this point we can use the results from previous sections to analyze the motion of these particles. Okay, we know that a is equal to dv by dt. So in principle, from this equation we can solve for the velocity of this object. Okay, and we also know that v is equal to the dr by dt. So once we solve for v, we have the result v here. We can then solve for the position of the particle. So at the end we should have the r as a function of t. Okay, so it means that when we know the force, in principle, if we know the force that act on an object, we can solve the Newton's second law to get the position of the particle as a function of time. There is a very useful concept when we use the Newton's second law to analyze our problem. It is the concept of the free body diagram. The free body diagram is the concept that you draw all force as a force vector that act on an object. And once you know all forces, you can use the second law to analyze, to calculate the acceleration, the velocity, and the position of the particle. Okay, so this is the most important step in solving the problem using Newton's law, is to draw a proper sketch, which this is the sketch of all forces that act on an object. That is the free body diagram. Be sure to draw only those forces that act on the object you are isolating. It means that you have to be careful and analyze what is the forces that involved with your problem. Be sure to draw all forces acting on the object, include any field forces such as gravitational force, because sometimes we can see obviously the contact force with the object, but we have to be careful that there may be some field forces in this. For example, they mentioned the gravitational force. later you may have the electromagnetic force and something more. So you have to be careful to put all forces on your free body diagram before continue calculate the acceleration, velocity, and the position of the particle. To summarize, we may say that there are two causes in our analysis. First, when the net force is zero, we can say that the particle is in equilibrium. For example, in this figure, a lamp suspended from a ceiling by a chain of negligible mass. This is an interesting point. At the beginning, we always say that the chain or the string has negligible negligible force. The negligible mass, not force, because we want to pay attention mainly on the object. So we will ignore the force of the string or the chain. But in the real situation, the chain, like in this example, has mass. So if you want to do the detailed calculation, you have to put the mass of the chain into your calculation, but it will make the calculation a little bit more complicated. So in the beginning here, we may neglect or ignore the the mass of the chain or the string by assuming that the mass of the chain or the string is negligible. And when you draw the free body diagram here, the free body diagram, that is, you have to think how many forces that act on this object. In this case, it's the lamp. You know that we have the gravitational force or the weight of the object. But if the lamp is in equilibrium, it means that it's not moved. So there must be another force that cancels the gravitational force. And in this case, we know that it is a tension in the chain. So you draw the gravitational force, you draw the tension, and these two forces cancel, and we say that the particle is in equilibrium. So we have that the net force in this case F is 0, okay, because the tension and the gravitational force cancel. And when the net force is 0, we have that A is 0 too, and the particle is in equilibrium. Okay. When A is 0, in general we have two cases of the equilibrium. First, we may call it the static equilibrium. The static equilibrium. The static equilibrium is the case when V is equal to 0. That is, the particle does not move. As in this case, you can see that the lamp hangs from the ceiling and is not moved. So the lamp is in the static equilibrium. We can also have the dynamic equilibrium. the dynamic equilibrium. That is, when the acceleration equal to 0, it means that we may have the situation that v is a constant, but it's not equal to 0. Not equal to 0. So in this case, the particle or the object move, but with a constant velocity, and we may say that it is in the dynamic equilibrium. Next, for the second class of the problem, if we have the case that is the net force is not equal to 0, so it means that the acceleration which equal to the net force divided by the mass is not 0. Again, you can write down the free body diagram. For example, this man tried to pull the object, the box is a wood box, and when you draw the free body diagram, we know that we have the force that this man pull the box, okay, and this force transmit to the box through the tension in the string or in the rope here, okay. So the first force that you may draw in the free body diagram is a tension in the string, okay, but the box is also under the gravity, or we have the gravitational force on the box too. So you have to draw this field force, the gravitational force on the box, okay. And since the box is not moved through the floor, so it means that there is the normal force that will cancel the gravitational force. So this is the third force that involved with this motion. If the surface has no friction, so we may have only these three forces, but if the surface has friction also, we have to draw the frictional force that we will discuss in the next section on this free body diagram also. So from this diagram you can see that we know that N and Fg cancel, so we have only T, the tension in the string, left. When you look at the free body diagram, you can see that the free body diagram will give you the free body diagram will give you the idea of the magnitude of the net force, and also it will give you the direction of the force, and this direction is also the direction of the acceleration.